We propose PLIKS, a pseudo-linear inverse kinematic solver for 3D human body estimation. PLIKS offers precise alignment to the input image, and it further enhances accuracy in 3D space by incorporating camera intrinsics during prediction. This consideration allows PLIKS to effectively handle perspective distortions that can arise from the camera lens used. In order to achieve precise alignment of the body mesh in 3D space, our first step is to estimate an approximate pose by predicting 3D vertices that align with the pixels. We then select different segments from the predicted vertices and their corresponding counterparts on the template SMPL mesh. By aligning these matched points, we can calculate the initial rotation centered around each segment. Next, we utilize PLIKS, which operates on 2D pixel-aligned vertices, to determine the optimal pose, shape, and translation. This is accomplished by solving a least square system derived from linearizing the SMPL formulation and incorporating the initial rough pose. By employing this method, our approach is capable of effectively addressing perspective warping, making it suitable for imposing constraints on shape or translation. In optimization-based techniques, we make assumptions about having prior knowledge of the joint locations of key points, along with camera parameters and a set of priors that represent plausible poses and shapes. These parameters are then optimized through iterative processes, often employing gradient descent methods. However, this approach faces a challenge of becoming trapped in local minima and generating unrealistic images. On the other hand, regression-based methods aim to directly regress the parameters by training on extensive datasets. The HMR method, for instance, starts by extracting global image encoder and subsequently predicts the model parameters using an iterative feedback loop module. It is important to note that the camera parameters it predicts are weak perspective parameters. Nevertheless, many previous approaches rely on the weak perspective model to estimate translation or scale factors. This method is generally feasible for deep learning and tends to be accurate when the subject is far away. However, perspective warping becomes apparent in images captured with a wide field when the subject is off-center or positioned too close to the camera. These factors can impact the final pose estimation made by the network. To address this issue, we aim to alleviate the problem by utilizing 2D vertex predictions on the image plane along with known camera parameters by solving a least squares problem. The pipeline of our architecture operates as follows. The network encoder generates predictions of pixel-aligned vertices, which are then fed into PLIKS to obtain optimal shape, pose, and translation. The mesh regressor responsible for predicting the vertices is based on I2L, mesh, net. Individual vertices in a pixel-based format. Our objective is to predict the SMPL model parameters using 2D pixel-aligned vertices, which requires reformulating the SMPL model. In this depiction, we exclude pose-related blend shapes from the SMPL model, and our focus is parameters highlighted in red. For the time being, let's assume that we have a reasonably accurate initial pose estimate, even though it may not be entirely precise. This assumption proves beneficial by narrowing down the search space. By leveraging this assumption, we can make use of the linearized rotation matrix, which is estimated through Taylor's expansion. This approximation is based on the notion that the optimal solution is in proximity. As a result, we are able to reframe the original SMPL formulation as a linear system of equations, which can now be resolved using the direct linear transform method. We can proceed to perform joint optimization for the parameters related to delta rotation, shape, and translation. The individual rotations can be determined by tracing the kinematic chain. Additionally, this process yields the translation in global coordinate. To establish the initial rotation, we extend the mesh regressor to predict in 3D. Using this initial prediction, we select various segments from both the predicted vertices and its corresponding counterpart from the template SMPL mesh. By aligning the matched points from the predicted 3D points and the template mesh, determine the optimal rotation. The results obtained on multiple datasets illustrate the robustness and accurate alignment achieved by PLIKS. Additionally, we demonstrate that PLIKS has the capability to generate improved absolute depth estimates, even though it was not explicitly trained to learn them. Agora serves as a synthetic benchmark encompassing a diverse range of cameras with varying field of view. Through our experiments, we demonstrate that our method performs exceptionally well in both 3D accuracy and 2D alignment when compared to prior method. Our constraint equation is designed to be expandable, allowing for the addition of multiple new constraints. As an example, we can switch from using the neutral SMPL model to the KID SMIL model for shape representation without the need for retraining. This versatility is demonstrated by applying the same model to children. However, it should be noted that the positioning of children can be somewhat ambiguous. To address this, we introduce translation constraints that enforce the z-depth of children to be similar to the predicted z-depth of adults. These constraints can be effectively utilized for motion correction, resulting in smoother pose deformation. Furthermore, they can be adapted for multi-view scenarios, expanding the applicability of our method. Here, we showcase qualitative results derived from PLIKS without any temporal smoothing. We appreciate your presence and kindly invite you to visit our poster for additional information.